for homework 4 of CS 294-137. My name is Ashwat, and let's get started. The purpose of the project is to create AR tracking and 3D reconstruction using images. So the first step is to create a camera calibration matrix, and to do this, we take images of a checkerboard, and it uses like corner detection to detect like the key points of this checkerboard. Using this, it's going to actually try to compute the camera intrinsic matrix. This is demonstrated over here, and essentially this represents the translation and scaling that the camera does, and it takes into account like the focal length parameters, center point, the distortion coefficients, and whatnot, and it determines the camera intrinsic matrix for the specific camera you're using. So this can be either the webcam of my laptop or the phone that I use to take images of, depending on the two parts. So going back to this, next step is to then use an AR image tracker. So this is the tracker that we used, and we have a real world version of this for which we know the dimensions. And the reason for this is we're going to do, essentially, we want to compute the pose of this image, the real world version, in the world from the camera. And to do this, we're going to do feature matching, in which it's going to try to compare points from the left, the digital image, to the right. And as such, you can see it over here. It's trying to compare them and do the matches that it sees visually between them. And the reason for this is using these matches, using the points, it can tell where the image is in the real world based on the pixels, and it knows what it's supposed to be, the correct size, and using all those parameters, it can compute the homography, which is like a perspective projection onto the real world, and essentially it can tell basically what is the pose of the AR tracker relative to the camera. And using this, we can accomplish a lot of features. One of the main thing being, once we do that, we can now project actual 3D points onto this image. So this video shows us essentially creating like a 3D cube and demonstrating that. So because it figured out the homography using the camera intrinsic matrix, we were able to overlay a cube and kind of project points onto the thing that we're tracking, the pose that we're getting of the tracker. So that's that. And the next step is now take and try to go to the reconstruction. So we're going to do the same thing, except now it's going to be a mobile camera, and we're going to take images. So again, using the AR tracker, we can compute the pose, and using multiple different images from multiple different perspectives, we can get different types of poses and know exactly like what the world looks like from the camera's perspective using the AR tracker. And we're going to do the exact same thing as before. And first of all, to show that it worked, we show the 3D cubes being overlaid. So again, we're able to correctly compute the homography. Then we're going to do the same type of feature matching between left and right images. So again, the left image is going to be fixed, and we're going to have the right image chain and kind of like match features that we see of this Kirkland box as well as the tracker between left and right. And we also further implement something called epipolar constraints, and essentially this works by kind of like comparing the matches between the two image points, and from the two different viewpoints, it kind of constrains them to be along a specific line, the epipolar line, in which matching points must lie. And as such, when they don't lie on this, when they fall below a certain threshold of 0.01, we're going to remove them because they no longer satisfy the epipolar constraint that we have between these two viewpoints. And that's why a lot of like the diagonal lines are now removed, because these images are showing it after the epipolar constraints have been exercised. So yeah, showing that this has worked. Ultimately, the next step is, now that we have the matches, we're going to figure out what is the depth of each of these points. And that is the last step. And we're going to do that by computing something called the M matrix here. And in this case, the M matrix is going to be what we use to like talk about the actual points. So in this M matrix, each of these rows represents like a feature in our image. So this is going to be the first feature. And for how many ever features, how many ever matches we have. So again, we're also constraining this based on the number of images that the same points match to. So we want to have certain matches to be at least on 3 or 4 different images, and that's how we know it's valid and like robust enough to use. So basically, for each of these points, if this is like one matching index from the original image, if we have 3 images showing this, we're gonna have 3 versions of this row. If we have 4 images showing this matched point, we're gonna have 4 versions of this row, all stacked together, each with homogeneous coordinates. So we're gonna make this huge matrix as such, using all the matches and all the images they match to. And then it's going to use this, and we want to compute the lambda using something called singular value decomposition. This is going to approximate the values for lambda, which represents the depths. And the code is here, the one that I created to essentially compute that. So I'm not going to go through for the sake of time, but this essentially is going to create the M matrix just like you see over here. And then using, again, svdcomp from the OpenCV library, we want to approximate the depths, approximate the value of lambda to get the depth for, again, 1-to-1 for each of the key points that we see. And now, once all that is all done and well, we're going to get the final output, which is going to be the actual reconstruction. So the image on the right is what we're trying to reconstruct, and the image on the left is the depth reconstruction using various points. You can see I'm highlighting the little red square on the bottom. This represents the AR tracker, which is pretty flat on the ground, as you can see. And then there's this colorful, like light-colored rainbow over here, and this represents the box. And you can know this is true because if you look at side view, you can see the AR tracker is flat on the ground, whereas the box is more vertical. So this shows that the code has overall worked. And yeah, that's about it for my presentation. Thank you so much for your time, and have a great day. Cheers.